Today we're going to be talking about applications of exponential and logarithmic equations. By the end of this video, you should be able to use formulas to solve real-world application problems. First, we have four different formulas here. The first one is the growth and decay formula. Usually has to do with bacteria or half-lives or some sort of sciencey application. You can see the equation here, and then it tells you what each of the variables represents. Next, we have appreciation and depreciation. That will typically have to do with assets, cars, houses, something that is increasing or decreasing in value. It's important to note here, there's a plus or minus. If something is increasing in value, you will use the plus. If it is decreasing in value, you will use the minus. Next, we have the compound interest formula. The formula, then it tells us what each of those variables represents. The one thing I want to point out here, n is the number of times that interest is compounded each year. So it's important to look at the words in the problem. If it says compounded monthly, there are 12 months in a year, so n would be 12. If it says compounded quarterly, 4 quarters in a year, so n would be 4, etc. Lastly, we have the continuously compounded interest formula. Again, we have the formula and what each of those variables represents. In general, in the last three formulas, the rate is always written as a decimal. So 8%, we would use the decimal 0.08, 12% you would use the decimal 0.12, etc. Our first problem says, suppose $500 is invested at 6% annual interest compounded twice a year. When will the investment be worth $1,000? So it's important to look for some keywords that tell us which formula to use. We are talking about compound interest, and it tells us that it's compounded twice per year. So we're going to use the compound interest formula. A is the final value, so that will be 1,000. P is the principal, or what you started with, which is $500. R is the rate, so we have 6%, so as a decimal, that's 0.06. N is the number of times interest is compounded each year, and it tells us that that's twice. And we're trying to solve for t. When you are solving these type of problems, the first thing you want to do is isolate the exponential. So we need to divide by 500. And I'm going to go ahead and simplify what is in the parenthesis. Then to solve this, you need to convert this to a logarithm. So I have log base 1.03 of 2 equals 2t. Then you divide by 2. It's important that you do not type this in the calculator until the final step. That way you do not have rounding error earlier in the problem. So now we can go ahead and put this in the calculator. If you go to math, go down to the bottom, you have log base. Here you can type a different base other than 10 or e. And we are going to round to 3 decimal places. So we have that it would take approximately 11.725 years. Since we're looking at word problems, it's important to make sure that we have units on our final answers. Let's look at another example. Suppose $500 is invested at 6% annual interest compounding continuously. When will the investment be worth $1,000? So this is almost identical to the previous problem, except that our interest is compounded continuously. So we want to use the continuous compounding interest formula. A is the new amount or the final amount of money, which in this case will be $1,000. P is the principal, or what we start with, which is 500. E is the number E. R is the rate, which is 0.06, and we're trying to solve for T. So, just like on the last problem, we want to start by dividing both sides by 500. And then, since our base of our exponential is e, we want to take the natural log of both sides. So I have natural log of 2 equals 0.06t. And then I can divide. Now I can go ahead and type this in the calculator. Natural log of 2 divided by 0.06. And again, we're going to round to 3 decimal places, so we have that it would be approximately 11.552 years. Now, if you notice, the only difference between this problem and the previous problem is that our interest is compounded continuously instead of twice per year. If you did several problems increasing the number of times that the interest is compounded, so in the previous example, n was 2. If you then increase n to 4, 10, 12, 50, 100, whatever, each time the time will be a tiny bit shorter. Here we're compounding the interest continuously, so that means you are redoing the calculations all of the time. And this is the fastest that you can get from $500 to $1,000 with an interest rate of 6%. Next, we have a certain type of organism can grow from 30 to 195 organisms in 5 hours. Find K for the growth formula. So first of all, it tells us that we are using the growth formula. We're also talking about some kind of organism, bacteria, something. So all of those things tell us that we are going to be using this formula. Now, Y is the final amount, or the final number of organisms, which is 195. N is the initial amount, or how many we start with. We're trying to solve for K. And it tells us that we are looking at a period of 5 hours. The way we solve this is going to be pretty much identical to the way we solved the last problem. We need to divide both sides by 30. That'll give us 6.5. Then, since the base of our exponential is e, we need to take the natural log of both sides and then divide by 5. Then we can type this in the calculator. And again, we're going to round to 3 decimal places, so we have 0.374. Now, K is a constant, so we do not have units. So this is our final answer. Next, we have an investment service promises to triple your money in 12 years. Assuming continuous compounding of interest, what rate of interest is needed? So it tells us we have continuous compounding of interest, which means we are using the continuously compounding interest formula. Now, here it does not tell us how much money we start with or how much money we end with, but it does tell us that we are trying to triple our money. So the easiest thing to do is assume that you start with $1 and that you end with $3. We're trying to solve for the rate, and we know that it takes 12 years. Now, since I picked starting with $1 and ending with $3, I do not have to divide by p. If you had picked another amount to start with, you would need to divide. Here I can just go ahead and take the natural log and divide. Then I can type this in the calculator. And I get 0.092. Since we are looking for the rate, if I take this decimal and change it back to a percent, I get about 9.2%. Here we have a slightly different problem. It tells us the United Nations created the following population model based on data from 1990 to 2002, and it gives us our function, where t is between 0 and 12. P is the population in billions of the world. T equals 0 represents 1990, and we want to know when the world population will reach 7 billion people. So, if we want to know when the world population is 7 billion, we need to plug 7 in for P. And we just solve like we have on the other problems. We need to start by dividing both sides by 5.451, which if you type that in the calculator, gives you 1.284, and the decimal continues. I'm not going to round this value here because that's going to make our final answer less accurate. So when I type things in the calculator, I will use the whole decimal. Then I need to take the natural log of both sides. And divide by 0.01165. Now, when I type this in the calculator, I'm going to type natural log of 7 divided by 5.451 divided by 0.01165. So I get, if I round to 3 decimal places, 21.469. And this is years. The question asks us when the world population will reach 7 billion people. It tells us that t equals 0 is 1990. So this answer means that we are looking 21.5 years after 1990. So what we need to do is take 1990, add 21, which gives us 2011. So sometime during 2011, the world population should hit 7 billion people. A quick Google search confirms that the world population did indeed hit 7 billion people during 2011. In this last problem, we're going to take a look at a different type of equation. Problem number 6 says, there is a college whose campus size is 5,000 students. One student has the flu. The spread of this flu is modeled by this equation, where t is given in days. How many students are infected after 5 days? And if the college policy is to cancel classes when 40% of the student body is sick, when will this happen? So this type of equation is called a logistic model. Couple things to note. The numerator tells you the carrying capacity, or the maximum value of the function. There are only 5,000 students on campus, so you can never have more than 5,000 students sick. So, part A says how many students are infected after 5 days. Well, this just means that we are plugging in 5 for t and evaluating our function. And then we just need to plug this in the calculator. I think it's helpful to use the fraction button for this problem. So if we have 5,000 divided by 1 plus 4,999, e, which we get from clicking second, natural log to the negative 0.8 times 5. Now, since we are talking about number of infected people, we are going to round to the nearest whole number. So we have 54 students infected. If the college policy is to cancel classes when 40% of the student body is sick, when will this happen? First, we need to know what 40% of the student body is. So, if we do 40% as a decimal times the total population, that gives us 2,000. So we need to know when there are 2,000 students sick. So we need to plug in 2,000 for y, and solve for t. First thing we need to do is multiply both sides of the equation by the denominator of the fraction, which would give us all of this stuff times 2,000. I'm going to go ahead and do 2 steps at once, multiply, and then divide both sides by 2,000. $5,000 divided by 2,000 is 2.5. Then we need to isolate the exponential, so we need to subtract 1 and divide by 4,999, which gives us 0.0003, and the decimal continues. Then we need to take the natural log of both sides, and divide by negative 0.8. So then if we go to our calculator, So that decimal that I wrote out that was 0.003, etc., is 2.5 minus 1 divided by 4,999. So we have natural log of this number divided by negative 0.8. If we round to 3 decimal places, we have 10.139 days. So it would take about 10 days for 40% of the student body to become sick with the flu. The one downfall of this model is it does not take into account people getting better and recovering from the flu. That would be a much more complicated example.